If you optimize the wrong loss, your ranking will never improve. NDCG-focused learning fixes the alignment. You will leave this video able to see how ranking quality maps to specific score updates, and to run a tiny LambdaRank-style loop that raises NDCG on a single query. I'm Professor Pi, teaching search and IR with simple Python. Ranking problems are everywhere. Search engines and recommender systems need the most useful items at the top. Traditional losses treat every prediction equally, but users only look at the first few results. Learning to rank with NDCG optimization solves that mismatch by aligning model updates with what actually matters to users. Success looks like better top 3 or top 5 relevance, rather than a lower average error. At a high level, NDCG is a graded relevance metric that discounts lower ranks. The core intuition is simple. Moving a highly relevant document from rank 5 to rank 1 is much more valuable than swapping 2 irrelevant ones at the bottom. Lambda-style methods turn that intuition into updates by computing the change in NDCG for possible swaps, and using that change to weight pairwise score adjustments. We will build a tiny, transparent example that shows the full loop. You will compute baseline NDCG, measure how much a single swap would help the metric, apply a targeted score update based on that gain, and repeat to see NDCG rise. No complex libraries, just the idea so you can scale it later. Now, we'll compute a baseline NDCG. This snippet measures ranking quality by computing NDCG on a tiny single query setup. The list rel holds graded relevance labels, and the list s contains initial predicted scores. The variable o stores document indices sorted by s in descending order to represent the current ranking. The expression for DCG applies the 2 to the rel minus 1 gain, and discounts by log 2 of the rank plus 1 using math.log2. The ideal IDCG is computed by sorting rel itself in descending order and applying the same discounting. Finally, the ratio DCG over IDCG yields NDCG, reflecting how close the current ranking is to the ideal. The printed value shows the baseline quality of the given scores. Next, we will quantify the impact of fixing one wrong order. This example quantifies how much NDCG would improve if we corrected a specific misorder. We pick positions I and J from the current permutation O and map them to documents A and B. The variables GA and GB compute gains using the 2 to the relevance minus 1 convention, while DI and DJ are position discounts derived with math.log2. We compute the local DCG contribution before and after a hypothetical swap, and normalize by IDCG to obtain a delta NDCG. This gives a precise impact estimate for fixing that pair. The printed delta shows the measurable benefit of correcting this specific inversion. Now we make a single targeted update using that delta. This code performs a single LambdaRank-style score update on the misordered pair. The probability P uses a logistic function of the score difference to softly reflect pairwise preference. The variable lam scales this preference by sig and the absolute delta NDCG so that larger metric gains push harder. We then decrease the lower relevance document score SA and increase the higher relevance document score SB using the learning rate LR. The updated scores are resorted into O, and the new DCG is computed with the same mathlog2 discounts to obtain a fresh NDCG. The printed value shows a visible improvement after one targeted step. Next, we try a gentler push to see how update strength affects competition for the top spot. This snippet explores a pragmatic tweak by reducing the push magnitude via a smaller sigma and step size. The probability P again uses the logistic on the same pair, and Lambda scales with a milder factor to avoid aggressive reorders. We then apply a smaller symmetric update to SA and SB, which nudges scores without fully flipping ranks. The variable margin measures S at document 0 minus S at document 2, a compact indicator of how the tweak affects competition for the top spot. Increasing sigma, or the step multiplier, steepens updates and widens this margin faster. The printed margin confirms a controlled directional shift. Finally, we target another inversion to complete a short training pass. This example targets a lower ranked inversion to complete a tiny but working LambdaRank-style baseline. We pick adjacent positions I2 and J2 from the previous ordering O, derive their gains GA and GB, and compute the delta NDCG term D2 using math.log2 discounts. The logistic probability P2 translates the current score gap into a smooth gradient weight, and LAM2 scales it up to enact a decisive correction. We then apply a symmetric update to the two scores and recompute the ranking and NDCG. The printed final value shows an additional measurable improvement, illustrating how repeated Lambda-driven fixes lift the evaluation metric. This toy loop maps cleanly to a real project. Replace the single query with mini batches of queries, compute deltas for a few high-impact pairs per query, and accumulate updates into a model like a gradient-boosted tree or a small neural network. The same metric-weighted pairwise signal drives the learning, even at scale. Recap. What it is: a metric-aware ranking update that weights pairwise changes by their NDCG impact. When to use it: when you care about top K relevance more than average error. One caveat: computing exact deltas can be expensive at scale, so you often approximate or focus on high-impact pairs. Next step: tune the sigma or step multiplier to balance aggressive flips against stable learning on a larger validation set. If practical IR work helps your projects, subscribe and watch the other IR videos.